All right. So we're live again on day 2 at JEC Jack World 2026. And joining me is Philipp Huber of Fenix Composites. One of the fascinating innovations here at JEC World combines thermoplastic composites with additive manufacturing. Fenix Composites has developed a bicycle frame that uses thermoplastic carbon fiber tubes and 3D printed titanium lugs joined by induction heating, creating a structure that can be actually assembled and or disassembled and repaired. So this is very unique for this type of application or industry. So Philip, thanks for joining me today on the podcast.
Thanks for having me.
So we were talking, before we went live. I want you to share a little bit about your background because I know you're a huge cyclist, but that's not how you got into composites.
No, actually, it's quite a big, complicated story, but I try to keep it short. So I was sailing my whole life, and I was also doing regattas and so on.
Yeah.
And most boats are at GFRP, but when you go into the really racing scene, then obviously CFRP becomes a big thing.
Sure.
And actually, I was just dreaming about the whole topic. About new components for the boat and so on. And then the question appeared about the recycling and so on, and that sparked curiosity, and I got into the whole thing of carbon fiber recycling and started to do my first projects. So first thing we built was a spinnaker pull from recycled carbon fiber stable fiber yarns, and because I wanted to test more, I built my own filament grinder, and I had some issues with the programming at the beginning, and then I was so annoyed that I said, okay, when this I don't want to drop an F-bomb. So when the stuff is working, I'm going to build a bike from the tubes. So I built my first bike with the filament round tubes, and I laminated the lugs from recycled carbon fiber non-wovens. And I was again so annoyed because laminating by hand, so I printed 3D molds, and then you have to create the molds, and some lugs are really complicated.
Right.
So design of the molds is really complicated. And
so you're 3D printing the lugs.
And then I had to sand everything, and so and then I was like, okay, next time I will just 3D print the lugs. And then also I realized, okay, I used recycled carbon fibers, but it's not recyclable because it's still a thermoset frame, and I have the same issues as every thermoset frame. And then the idea was, okay, we use thermoplastics because then we can heat it, it gets viscous, and then you can pull off the defect part. And that was the easy part of the idea. The more complicated part was the question how we actually create the joint. First, I was thinking about macroscopic interlocks, but then somebody from HighJoint contacted me, and they said, we might have the right technology for you. And that's where we started the development to adjusting this thermal direct joining process to CFRP tubes.
Okay.
And that was the basis to build the bike. So I tried to keep it short, but it's a long story.
No, so you built your own filament winder. That's that's pretty incredible.
But just 2 axes. So you have the mandrel that spins and the traverse that runs, but most parts were also 3D printed, and it was running on an Arduino. But actually the tubes, after I understood how to really make the tubes looked better than some parts that some companies are brave enough to present here.
Right.
So
what's been the feedback so far that in talking with people about this?
So it's really interesting because the feedback is good, let's say. People think it's a great idea, but I'm still unsure So between it's interesting and we think it's cool, and we are actually going to buy this. That are two different things. At the beginning, when I started to look at creating a known company, this was always something I struggled with, because I thought, okay, people think something is cool, so they are going to buy, but this isn't necessarily the case. But if you go to the Innovation Planet, you see that there's always a big crowd around the bike, which is like really, really awesome,
Right.
because I built it and it makes me proud of this.
Absolutely. So the frame we're talking on this frame, it uses heating to melt the thermoplastic, induction heating to melt the thermoplastic and bond the tubes.
Yeah.
So the joining process, what advantages do you see, or are you highlighting compared to traditional bonding methods?
Yeah. So first, a small explanation. We have a microstructure on the joining interface of the metal. So there's like grooves cut with a laser, for example.
Sure.
And then the polymer flows into the screws, and this creates the interlock. And one of the key advantages is that the joints are really, really strong. I think the reference value for adhesive bonding is 13 megapascals of shear strength.
Okay.
And we managed to achieve over 50 megapascals with nylon 6.
Okay.
So we are like 50% above the industry standard. And this means you can create shorter overlaps. Actually, we have this tie rod, and the overlap is so short that you really need to be careful that your insert doesn't tilt while putting it in, because when it's longer, it aligns itself. But so, and the other thing is the cycle time. We heat for maybe 2 to 3 seconds, and then the part needs to cool down, and then it's ready to use. If you look again at adhesive bonding and you have to cure the part afterwards, if you don't cure it, curing takes a day, and then full strength comes after a week. If you cure it in an oven, it takes still hours. And here we have.
So you're heating and then cooling that down, and that takes a time frame of.
Yeah, we heat for maximum 10 seconds, then it takes 5 to 10 minutes, depending on the part size, to cool down. And then it's ready to use. So that is really good. And it's also pretty cheap. I mean, the joining energy is so low because it's really only on the joining interface. If you put the part, we only heat the actual joint, because if you need to cure in an oven, you don't heat the joint, you heat the whole part, you heat the air, you heat the isolation, so you lose a lot of energy. And to create the joints, we have energy costs of, so we have energy consumption of a fraction of a kilowatt hour, which results in energy cost of a fraction of a cent, which is really ridiculous, and also brings you a really, really low CO2 footprint. So we talk about 3 grams of CO2 emissions from the energy perspective for a single joint. And then if you look at the repair case, you need the same amount of cost to unjoin the part. And if we look at the tie rod, the tube is around 90 euros, the titanium parts are 90 euros, and if the tube breaks, you invest around about a cent of energy cost to get your expensive titanium back, and you can use it, you can create a stronger tube, for example, and then you can heat the joint for another cent of energy cost. So I think it's from an economic point of view, it's like a no-brainer in my opinion. But
so do you see the joining technology? I mean, would it be your goal to push it into other, outside of just the cycling, the carbon fiber thermoplastic bikes? Would you like to see this into go into other industries as well?
Yeah, actually that is kind of the goal, because I think the cycling market is really, really tough, and I think it's, even if you have a unique USP, it's still really, really difficult.
It's a challenge.
But I think what the bike is really good for. It's fantastic marketing because everybody understands the bike.
It's a good test to start with.
And you can also test a lot of it. So you can try different things and you also get an understanding of fatigue behavior. So it's a really good prototyping use case. And the idea is then to move into also more simple to manufacture applications, like because on a bike you have different tube diameters in different joining positions, and also you have the whole assembly and you have to connect several. During pre-assembly you have several connections that need to be moved at the same time to fit everything together. And if you look at something like tie rods or drive shafts, it's much more simple and easier to automate the pre-assembly because you have a straight tube and at the end you have your metal part and then you can push it together, join it, and this is much easier to to automate. And if you really automate it and look at the cycle times, you get at the production output where you have more to worry about getting enough material that you can actually join, because if you run the process continuously, for example, I was looking at one series of BMW's production where they used CFOP drive shafts, and you can manufacture the whole batch in 4 months, and then you need to think what you do the other 8 months of the year. So there's huge potential from.
So automotive would be a fantastic.
Or helicopter drive shafts. So the main idea is right now to use the technology and go into just focus on tube functionalization with metal inserts and stay on the 3D printing path and combine it with topology optimization.
So this was on a cycling bike, correct? Cycling?
Yeah.
Okay. Because I was thinking, I don't know how big mountain biking is in Germany, but it's big in the States. People love mountain biking, and they put a lot of stress on those bikes.
Yeah, I know. Well, for me, it's always I love traditional road cycling, and I think I could also go into mountain bikes, but I don't ride it. I don't understand it, and actually, it's also more complicated when you also have to handle suspension and so on.
Of course, yeah.
So these are things. I don't want to do something where I'm not 100% behind it.
Absolutely. Well, you start with what you know and what you're familiar with. And you going back to the lugs, you printed these yourself on your own printer?
No.
Oh, okay.
It would be really amazing to have a metal printer that prints titanium, but I think it's a little bit out of budget.
A little expensive at this point, but not, maybe in the near future.
I'm also dreaming of my own AFP head, but there's still some time to go.
Well, congratulations again on the Innovation Award, being a part of that, and best of luck tonight for you. So it's great to talk with you, and I hope we can talk again soon in the future.
I hope so too.
I'd love to follow up on your success. So thanks again, Philip.
Thank you for having me.
Absolutely.